Building language models used to be about fine-tuning static weights. Today, scaling to production requires mastering inference-time compute and distributed hardware scaling. Large language model generation operates in two distinct phases. The prephase phase processes the initial prompt and is compute-bound, meaning it is limited by the raw mathematical throughput of the GPU. The decode phase generates new tokens one by one and is memory-bound, bottlenecked by how fast data moves from storage to the processing cores. Autoregressive generation creates a structural paradox. The mathematical weights of the model remain static, but the key value cache, the memory storing the context of all previous tokens, grows dynamically with every single token generated. This calculates the memory footprint per token, 2 times the model's layers, attention heads, head dimension, and precision. Applied to a 70 billion parameter model with a 2 million token context, this p-value cache instantly exceeds the video RAM of an entire high-end GPU cluster. Because scaling context mathematically guarantees memory failure on standard hardware configurations, engineers must rebuild the inference architecture from first principles. This illustrates standard contiguous memory allocation. Traditional frameworks reserve a rigid memory block for the maximum possible sequence length, leaving huge portions empty. This internal fragmentation fills the hardware with blank space, capping the number of requests a GPU can serve at once. The first architectural fix is page detention. Page detention borrows the concept of virtual memory mapping from traditional operating systems and applies it to language models. Instead of one continuous block, the cache is sharded into fixed-sized blocks. A block table routes the logical sequence to scattered physical memory blocks. This fragmented mapping enables copy-on-write semantics. Multiple users route requests to the exact same cached blocks, eliminating duplicated padding. While raw compute still dictates the speed of the initial prefill, the serving capacity during the decode phase depends on how effectively the engine shards and reclaims this memory. Optimizing memory allocation is only one part of the problem. The next step is optimizing numerical precision. On NVIDIA's Hopper architecture, 8-bit floating point, or FP8, is the standard for efficient computation. Operating in 8-bit requires a strict mathematical trade-off at the bit level, balancing dynamic range, the span between the largest and smallest possible numbers, against precision, the exactness of those numbers. This bit-level diagram compares two dominant 8-bit formats. E4M3 allocates 3 mantissa bits, preserving fine nuances of weights and activations. E5M2 drops a mantissa bit for 5 exponent bits. Gradient calculations and outliers strictly require this wider range to prevent overflowing hardware limits. Selecting the correct 8-bit configuration effectively doubles the processing throughput of an H100 GPU over standard 16-bit operations. Manipulating bit-level architecture cuts the memory footprint in half while keeping accuracy degradation below 1%. With the memory mapped and the numbers compressed, the architecture must shrink the data payload itself. This is achieved through multi-head latent attention, or MLA. Standard multi-head attention duplicates the key value cache across numerous parallel heads, scaling memory costs linearly. MLA alters this by projecting keys and values into a shared low-dimensional space. This compression reduces cache requirements by 93.3%, expanding back only at the moment of calculation. At the hardware execution layer, standard kernels waste time waiting for data to travel from high-bandwidth memory into the GPU's internal static RAM. Flash Attention 3 masks this transfer latency. By utilizing producer-consumer asynchronous warp scheduling, producer blocks pull data continuously, while separate consumer blocks simultaneously execute math on the tensor cores. Shrinking the latent space while interleaving memory transfers with compute allows a single GPU to operate closer to its theoretical maximum utilization. Building trillion-parameter models requires moving past single-device logic. They demand a massive cluster topology managed by 5D parallelism. 5D parallelism is a multidimensional mesh that distributes the workload across 5 axes: data, tensor, pipeline, sequence, and expert parallelism. This pipeline chart exposes the fetal flaw of pipeline parallelism, the bubble. Hardware sits idle waiting for previous stages to finish. To solve this, architects use one forward, one backward scheduling, or 1F1B. One F1B interleaves new forward passes with older backward updates, filling idle gaps and maximizing utilization. When the token sequence length exceeds a single GPU's memory, standard data parallelism breaks down. Scaling to massive context lengths requires context parallelism, utilizing a routing logic known as ring attention. In ring attention, each GPU computes a local chunk of tokens. It then passes its key value blocks to its neighbor in a continuous circular network to compute the global matrix. Cluster-scale inference operates by orchestrating a multi-dimensional mesh where network communication is hidden behind ongoing computation. Advanced reasoning models utilize reinforcement learning to evaluate their own logic, which introduces massive memory overheads to the cluster. This system architecture diagram displays standard reinforcement learning from human feedback, or RLHF. It requires a massive critic model to predict state values, effectively doubling the VRAM requirement of the system. Group Relative Policy Optimization, or GRPO, breaks this dependency. It calculates the advantage signals strictly relative to the mean and standard deviation of generated samples. By deriving the signal mathematically, it eliminates the critic model entirely. Removing the critic instantly frees up to 50% of the system's total VRAM, while providing a stable reward signal for binary reasoning logic. With the memory footprint minimized and the architecture scaled, the final engineering decision is selecting the production inference engine. Engines like VLLM operate as general-purpose serving layers. They are ideal for rapid deployment, multimodal flexibility, and leveraging a large open-source ecosystem. This comparison matrix highlights the alternative, TensorRT LLM. Rather than serving, it acts as a hardware-optimized compiler, designed for hyperscale, fixed hardware environments. TensorRT LLM utilizes deep kernel fusion to yield an extra 20 to 40% throughput on specific hardware, translating directly to significant cost savings at scale. Architecting a production-ready system requires a precise balance between accuracy, latency, and cost. Mastering these inference time compute laws provides the technical foundation to lead the next generation of architectural breakthroughs.